Welcome back to Physics 141 Online. Before moving on to the next section of the course, which will start in Chapter 4 with a discussion of Newton's laws of motion, I'd like to wrap up our discussion of two- and three-dimensional motion by just re-emphasizing the problem-solving steps that I would like to see you use in your homework assignments. This is, again, the IDEA method. So, interpret. We begin with some understanding of what the problem involves. And here we're talking about free fall motion with a constant downward acceleration and the balls hitting the ground at the same time. This step will usually also involve a sketch that should at least show the initial situation. And in some problems it would be good to show the final situation as well. Develop. We want to develop a plan of attack. And here I've identified that I want to use an equation involving the given quantities, and it's very important here, write a separate equation for each ball and then combine those equations in order to solve for the unknown initial velocity. Here, I'm not too concerned with going through all of the details, but now I move on to the evaluation step where the equations are used. We plug in the given quantities, even though they're symbolic quantities, we plug them in. We then combine the equation for ball number 1 and ball number 2, and we solve for the time. And I put a little box around it because although it's not the final answer, it is an important intermediate answer. Then we use that to find this initial downward velocity. And so that is the final answer, but it's not the end of the problem because there's still the assess step. And I was able to assess both the sign of the answer and, again, the units to see if they made sense. There were no numerical values to assess, but still we were able to check the answer to see if it was reasonable. So please, get in the habit of using these steps on your homework assignments. One more thing then that I'll also mention is that in these solutions you should make sure you always do certain things. Draw clear and large sketches. There's no prize for the smallest possible sketch that you can squeeze onto a small space on your page. So make them large enough so you can see the details. Leave plenty of space between steps on the page. Once again, there's no prize for the student who completes the homework assignment using the fewest number of sheets of paper. Explain what you're doing. Use words in your problem solution, not just a bunch of equations. One of my favorite things to do is to number the different equations that I write down, and then when I do combine them, I can write down something like plug t from equation number 1 into equation number 2. And it helps me and my student grader when we're looking at homework papers to understand what you're doing, and it will also help you when you go back and look at that paper later to prepare for a test, to figure out what you were thinking when you solved the problem. And there are parts of problems where you may have to explain your results, particularly if you make a choice. If you have a quadratic formula and you use that to solve for a given quantity, like the time, there may be two possible answers because there's the plus or minus sign in the solution to the quadratic equation, and you should explain why one of those results is the one you're choosing and why the other one doesn't make sense. So always go through those kinds of steps. It makes it much easier for me to understand what you're doing. Remember once again the old adage I mentioned that came from my freshman physics book. The only problems that are really worth doing are the ones that sometimes hit back. And so that's not too surprising when we're doing physics problems. And this one, I think, is also important to remember. It's a great quote from over 100 years ago by a scientist named Charles Dutton, and he said, "Subjects which disclose their full power, meaning, and beauty as soon as they are presented to the mind have very little of those qualities to disclose." In other words, the things that are obvious the first time you look at them really don't have very much content to them. But a subject like meteorology or physics or chemistry or engineering that takes time to understand, that only over time do we really begin to appreciate the power, the meaning, the beauty of those subjects. These are the things that are really worth studying. And so I feel that way about physics. All right, now we're going to move on to talk about information from Chapter 4. We're dealing with Newton's laws of motion. So, here's the outline for the section, and we're going to start with the relationship between kinematics and mechanics. which are related but are actually separate subjects within physics, and move on to Newton's laws of motion. Finally, we'll talk about common forces in nature, and then just do lots and lots of practice solving problems using Newton's laws. Somewhere along the way, we'll make the transition into Chapter 5, where special kinds of situations are introduced involving frictional forces and also involving circular motion. But this really forms one unit that in our textbook is broken into chapters 4 and 5. So kinematics is concerned with the relationship between position, velocity, and acceleration, and time, of course. I didn't write that down, but time as well, for an object without really reference to the origin or the reason for the motion. We're just watching a car move down the street, or we're watching a ball roll down an inclined plane, or something like that. We don't really worry about what causes the motion. We simply observe it and describe the relationships between these quantities. Now, mechanics, on the other hand, is the study of the relationship between the forces that act on the object and the subsequent motion that arises from those forces. And see, mechanics gets at the causes. What is it that we do to an object to change its state of motion? And this is where Newton's laws of motion come into play. So, from the time of the Greeks until almost the time of Galileo in the early 1600s, people regarded the natural state of an object as being at rest. And so, because of that, they assumed that there was a direct connection between the force on an object and the object's motion. So, in other words, they reasoned like this. If an object is moving, there must be a force acting on it, because else why would it move? So if they had thought in terms of equations, the way that we do in our course, they would have tried to develop an equation between the force on an object and between its motion, which is described quantitatively by its velocity. And they often tried to do this. And it was a very natural thing to do. But it's also very misleading. And we see it today as being wrong. The reason that they thought this way was that, well, a non-zero force, they thought, implied a non-zero velocity, and vice versa, right? If an object's moving, there must be a force acting on it. The great contribution of Galileo and Newton in the history of science, and what we now think of as mechanics, is they showed that this is wrong. And yet, even today, most of us, even many physics students, still think that this is true. So I hope to show you in this section of the course why it's not true. The actual connection is not between force and velocity, or force and the motion of an object, but force and the change of an object's motion. Galileo was the first one to take steps in this direction. Of course, there were some people before him who had some idea that the Greeks were wrong about this. But Galileo was the first one to really do demonstrations to show it. Galileo's contribution lied in carrying out thought experiments, where he imagined simple physical situations that allowed him to figure out the causal relationships between forces and motion. And what he realized, and as I understand it, Galileo imagined that you could have a chunk of ice that you would throw across a frozen lake, where it would encounter very little, if any, frictional force. So Galileo realized, by thinking about things like that, that a moving object, which actually seems to slow down, because as objects move, if we wait long enough, we observe them slow down. Imagine a book sliding across the surface of a table. Galileo realized that those objects actually would not slow down if there weren't frictional forces between that object and the surface it's moving on. And so he was able to come up with this intuition that forces don't cause motion, but they cause the change in motion. Frictional forces cause things to slow down and eventually stop. Newton, on the other hand, was able to take Galileo's insights. It's interesting that you see Galileo died in 1642, which was the same year Newton was born. And when Newton was in his late teens, as a college student, he developed ideas that later resulted in some of the most profound mathematical books of the 17th century. And so Newton was a genius both in math and physics. He was the co-inventor, along with Leibniz, of calculus, and he discovered the inverse square law of universal gravitation. And his ideas, written down in what we call the laws of motion, are the basis for our subject here. So, first law, what does that mean? Here we realize formally that the connection that's proper to draw is not between force and velocity, but between force and a change in velocity. And here was the first law, which is actually written down first in an early form by Galileo. The idea is that an object moves with constant velocity, and that means it could also remain at rest, because rest is a situation of a constant zero velocity. But the object moves with constant velocity unless acted upon by a net external force. So, if you turn it around, what it says is, if an object is acted upon by a net external force, it cannot move with constant velocity. Its velocity actually changes. Okay? This is also called the law of inertia, because inertia is a word that refers to a property of matter that makes it resist being accelerated. It resists having a change in its motion. So the principle assumes that the proper connection, this is the cornerstone of modern physics, is between the force acting on an object, the net force, and the change in the object's motion. In other words, the change in its velocity, which is quantified by the acceleration. So, beginning with Newton, we now look for a relationship between the net force on an object and its acceleration. So, if an object moves with constant velocity, if we know that, we watch an object moving along a particular direction, and if it's moving with constant velocity, with an unchanging speed and an unchanging direction, then the net external force acting on it is zero, because constant velocity means no acceleration. This is really unusual, right? This is something that our common sense experience seems to argue against, and the Greeks, had this idea too. They thought that if an object moves with constant velocity, it must be experiencing a force. But it's actually not true. The net force must be zero. The second law quantifies the relationship that comes from the first law. It says that the acceleration of an object is in the direction of the net force it experiences, and it's inversely proportional to its mass. And the mass is a measure of the object's inertia, or its resistance to acceleration. So writing this down in equation form, we say the acceleration is in the direction of the net force, and it's inversely proportional to the mass. So the acceleration is equal to the net force. This is a summation of individual forces. Forces have direction, so that means they're vectors. So we add up all the individual forces to get the net force, divide by the mass, and that gives us the acceleration. And a lot of times we turn this around and we solve for the net force and set that equal to the mass times the acceleration. That is Newton's second law. Some people say it's just F equals ma, which is partially true. The F in that equation actually represents the net force, and that's why I will always write this with a summation. So, it's really a way of defining mass as the proportionality constant between the net force and the acceleration. The third law, which will be important in some of the problems that we work on, especially problems involving more than one object, third law says that all forces occur in equal and opposite pairs. And what it really means is, if an object A exerts a force on an object B, then it must always be true that object B exerts an equal and opposite force on object A. So what does this look like? If these two objects here, a ball and a block, are in contact with each other, then they exert forces on one another. So B exerts a force on A that is away from the surface of contact. That's what I've labeled here as FBA, the force of B on A. And they're touching, which also means that A exerts a force on B that is in the other direction. This is the force of A on B. And the third law says these forces must both be present and that they are equal and opposite in magnitude. Equal in magnitude, opposite in direction. So if we were to write down a relationship between them mathematically, we would say that the force of B on A is minus the force of A on B. They're minus because they're in opposite directions, but they're equal because their magnitudes are the same. And some books call these action-reaction pairs. So for example, if I have a hammer and I hit the head of a nail, the hammer exerts a force on the nail, right? And that causes the nail to accelerate briefly and go into the wood. But the nail also exerts a force on the hammer, slowing it down, changing its motion, right? And so those two forces are equal and opposite in direction. As I said, it's important then when we have two or more objects that exert forces on each other. So, one important qualification as we finish this section, where we've discussed qualitatively Newton's laws, is who is it that can write down Newton's laws? As we've stated them, and in particular it's the second law that's important here, Newton's laws are only valid in special reference frames, and these are non-accelerating frames of reference. Our textbook talks about inertial frames of reference, and that means that they are non-accelerating. So the accelerations and the forces that we use to write down these laws must be measured by an observer in an inertial reference frame. We will sometimes have problems involving objects in elevators, and as long as those if we want to describe the physics going on inside the elevator, we have to ask ourselves, is the elevator accelerating? And if the elevator is accelerating, up or down, then that means that we can't use Newton's laws to describe what an observer in the accelerator would see. We have to imagine ourselves stepping out of the accelerator, out of the elevator, and watching what's going on from a distance. Then we, as the observer who's not accelerating, can write down Newton's laws correctly. And so there are problems where that will become important. So in class, we will start to talk about common forces in nature and then use them in simple problems involving Newton's laws. I'll see you in class.